This is Neha Sinha with Lab 9 Spring Mass Systems. The main problem addressed in this lab is the transfers of energy in a spring mass system. I applied the momentum principle and the energy principle, as these are the models relevant to the physical system. Here in Tracker is a video of a mass hanging from a spring. The calibration stick was set to the length of the relaxed spring mass system. You can see the tracking of motion of the mass as it is pulled to the side, released, and allowed to move in the x and y directions. The mass of the weight on the spring is 0.402 kilograms. The initial position of the weight is shown here, found on the coordinate system whose origin is set at the top fixture point of the spring. The initial velocity of the mass is 0. The model starts at time 0. The spring constant is 6.86 kilograms times meters per second squared, found using the formula frequency is equal to omega over 2 pi. Frequency can be found by identifying the time of one cycle from Tracker, also called the period, and taking the inverse of this. Omega is the square root of the spring constant k over the mass. So the equation can be rewritten to solve for k. The relaxed length of the spring without the mass is 0.127 meters. This was found using Hooke's law. The force is negative mg, so this can be written to solve for x, which is L minus L naught, and solving for L naught produces this equation. Initial gravitational potential energy is mgh, calculated here. Initial kinetic energy is 0. The while loop in Python is set to last the length of the Tracker video, 8.452 seconds. Gravitational force is mg, L is the length of the spring with the mass. Here, S, the stretch of the spring is calculated. Here's the force of the spring using Hooke's law. The net force is gravitational force plus spring force. The momentum principle is applied to update velocity and position. Kinetic energy is 1/2 mv squared. Gravitational potential energy is mgh, and spring potential energy is 1/2 ks squared. Here, all energy calculations are updated. Time is updated here. And now here you can see the model in Python. Note that the yellow ball is represents the model data, and the blue ball is the experimental data from Tracker. The period of oscillation in Tracker can be found by isolating times at the start and end of a cycle. The final time minus the initial time gives the period. Here, the period is 1.52 seconds. In Python, the period of oscillation is found the same way, using the graph Python produces to find the final and initial times of one cycle. The period of oscillation in the y direction is 1.547 seconds. The period of oscillation in the x direction in Tracker is calculated to be 1.62 seconds. For Python, the period of oscillation in the x direction is 1.684 seconds. In comparing the periods of oscillation, it is apparent that the Python and Tracker data matches up. The difference for x is 0.06 seconds, and for y is only 0.02 seconds. Here are the graphs, which also display how well the oscillations match up in both Python and Tracker. For the first what does it mean question, it is clear that the x and y periods differ by 0.1 seconds. This is because, as seen here, the motion of the spring is elliptically shaped and slanted downwards, which shows it takes more time to move in the one cycle in the x direction than in the y direction. That being said, the 0.1 seconds is not extremely significant. The spring potential energy is 1/2 ks squared, graphed here because it oscillates with the spring because it depends on stretch. For the second what does it mean, the work done by the surroundings is equal to the change in energy. But because there is nothing in the surroundings but the earth, the spring, and the mass in the system, then work, and by extent change in energy, should be 0. Here are the calculations, and in fact, work is 0. Finally, for the last what does it mean question, if the origin is changed from the top of the spring to the mass on the spring at rest, these would be the new position vectors, with the ball position marking the initial position of the mass. Changing the origin does not change the physics of the system, however. These are the energy plots from before and after the change in origin. As you can see, they are the same. This is because changing the origin only changes the stretch, which is included in the equation for spring potential energy, but will not change the spring potential energy because the difference between L and L naught is the same. And that is my analysis of a spring mass system. Thank you for watching.